Good evening, everyone. Myself, Rachit Neema, IT-2K24-71. Today, I am going to present assignment 2 of numerical analysis and design. Here, we going to study about the 7 topics and their codes in Python. So, let's start with the first question. The first section we have root finding methods. We have 5 root finding methods: bisection, Regula-Falsi, secant, Newton, and fixed point iteration. Let's see their code one by one. First, we have bisection method. So first we take the assumption that f of a dot f of b should always less than 0, and if the sign changes, that means the uh, points lies between them. F is a continuous on a and b interval, and there is exactly one root in the interval. The geometric interpretation states that repetitively bisection intervals, root bracket at each steps, conversion is guaranteed. The time complexity for the following is order of log base 2 b minus a divided by tolerance, and the space complexity is order of 1. The conversion is linear but slow but reliable. Error half each iterations. Let's see the code. First we import the numpy as np. Then we create a function bisection for with the following parameters and argument: f, a, b, tolerance, and max iteration. We take max iteration by 100, so we can easily calculate this. In this, if a of f of a multiplied by f of b is greater than 0, then the f of a and f of b must have different opposite sign, and the error will raise. If it's not, then we continue with the loop where we calculate c for the bisection, and if absolute of c is less than tolerance, we return c and continue with the iteration. Else we initiate b equals to c and a equals to c, and return a plus b divided by 2, and use by using lambda function. Let's move on to the next second thing. We have Regula-Falsi method. The assumption we take in here is f of a dot f of b should be less than 0. F is continuous in a to b, and use linear interpolation. The geometrical interpretation states draw a line between them, a comma f of a and b comma f of b, and then use an X interpreter for the next pointer. It is faster than bisection. The time complexity is order of O, log A by tolerance, which is the average, and space complexity of order of n. The Python code is following. We take function. We take the input as parameters. We apply the first condition of sign change. If no sign change occurs, it returns a value error. Um, then we start with the max iteration by using the for loop, in which we calculate c by a into f of b minus b into f of a divided by f of b minus f of c. And if the absolute of f of c is less than tolerance, will return the c. Else we will substitute b equals to c or a equals to c. We call this by using lambda function, and so on. Let's move on to the next method. Next method, we have secant method. Secant method assumption we take, we have two distinguished initial guesses. F is differentiable near roots, and f of x0 is not equal to f of x1. The geometric interpretation, we have secant line through 2 points. X interpretation is equal to next iteration, and no background is required. The time complexity for the same is order of log 1 by tolerance. The space complexity is order of 1, and the conversion is superlined. The code is such as: we create a function secant, we take the input as parameters, we continue with a loop for the max iteration, in which we take f of 0 and f of 1 equals to f of 0 and f of 1. We initiate these both, and we calculate if the absolute of f of 1 minus f of 0 is less than tolerance, then we raise a zero value error where denominator is 0. The secant formula updated: x2 equals to x1 minus f of x1 into x1 minus x0 divided by f of x1 minus f of x0. And then we calculate absolute x2 minus x1. If it is less than tolerance, we return the x2 as the result, and continue with the iteration. we use this as a lambda function by calling in the main function. Let's move on to the next point. We have Newton-Raphson here. Newton-Raphson method states the assumption we take is f and f dash are continuous. F dash of x is not equal to 0 and the initial guess should be good guess, else we will not able to find iterations. The geometrical interpretation we have is we follow a tangent line at xn and f of xn. X interpretation equals to new iteration, and xn plus 1 is equal to xn minus f of xn divided by f dash of xn as a geometrical formula. The time complexity is order of log 1 by e and space complexity of order of n. The conversion is not guaranteed, but it is the fastest way to find root. The code we have is we initiate a function with taking input as all parameters. We initiate x equals to x0 and we run a loop for max iteration. F of x equals to f of x. If the absolute fx is less than tolerance, we return the x as the result, or d of dfx is should be equals to differentiation of x, where absolute of dfx should be less than tolerance. If this condition is true, we raise a zero division error where derivative 0. X equals to x minus f of x divided by d of x, the Newton updated formula. We call this using lambda function in the main block. Let's move on the last iterative method, which is fixed point iteration method. The assumption we take here is f of x equals to 0 and it's only work when g dash of x absolute is less than 1, which is near root, and the initial choices should be good. The geometrical interpretation states that y should be g of f of x, where intersection between y equals to x. The time complexity for the following is order of log 1 by e tolerance and space complexity of order of 1. Conversion. Conversion rate is not fixed, but it is slow, but has a simple code. The code is following as we create a function, take input as an argument, we initialize x equals to x0 and we initialize history as an array. We run the loop for the max iteration and use x underscore new to apply g and history dot append g into the array. If the absolute of g x new minus x is greater than tolerance, we return x new and continue with the loop. And x equals to x1 and continue the loop, and we call using the lambda function. This second section we have interpolation techniques, in which we conquer Lagrange, Hermite, divide difference table, and Newton formula. Let's start with the Lagrange. The Lagrange interpolation, the assumption here we take is n plus 1 is the distinct data point. The point should be x0 and y0 to the xn to the yn. There should be no repeated x value should be there. Hence we get zero error. Geometrical interpretation, unique polynomial of degree less than n. The path should through all n plus 1. Basic polynomial L of I should be equal to 1 at ixi. The time complexity is order of n square and space complexity of order n. Let's see the code. We import numpy as np for the array thing, and we have the code, the function. We take all the required thing as an argument in here. We initialize is result with 0 and length with n. We run the loop for in the range n and compute the ith basis with li is equals to 1, and again we use a nested loop for j to the n. If j is not equal to I, we will run the following code and save the stored result in the result variable and return the result variable. We call the function in the main point by giving all our required value, and hence we get the result for the Lagrange interpolation. Let's move on to the next. It's Hermite interpolation. Same with assumes data should be xi, yi, y dash I. Both value and derivative should be known. Distinguish x point. The geometrical interpretation is matching value and scope. A uniquely poly of degree 2n plus 1. Smooth it is smoother than Lagrange interpolation. The time complexity here is order of n square, and space complexity is also order of n square. Here we have code such as we import numpy, we create the function, take all the required thing as an argument, we initiate n equals to the length of x point, and then we take two variables z and q. Z should be repetitive point and q should be zeros point. We run a loop with the range n and compute these all required thing. If I is greater than 0, we will calculate q2 into I comma I, and for j in range 2 comma 2 into n, we will compute that and evaluate all, and hence we get the result for Hermite interpolation. Let's move on to the next question. The next question states that divide difference table. Here we need to create divide difference table. So let's directly jump on the code. Here we import numpy as np. We write the function, take x and y as an input for the divide difference table. We define n is equal to the length of x. We define f for all the 0 in n comma n, and run the loop j in the range I comma n. For I in range n minus 1, f of I comma j should be equal to f of I plus j comma j minus I minus f of I comma j minus I, which is divide and return f as a result. And then we create another function is Newton interpolation, and with the value x comma y comma well should we get from the upper value. Here we do the same thing and run a loop, and we store the product in product variable. Product is multiplied by equal to value minus x I minus 1, and result in the result variable, and result return the result for the function. We call in the main function and we'll get the divide difference table. The time complexity for this is order of n square, and space complexity is order of n square. Now we have forward and backward table. Similar to the previous difference table, we use that difference table in for the following forward and backward difference table. Here we have complexity of order of n square and space complexity of order of n square. The geometrical interpretation for forward is lambda y equals to y1 minus y1, and nebula y equals to yn minus yn minus 1. The forward and backward. The code is such as we create two function, forward difference table and backward difference table. With the y, we initialize n to the length, we initialize table zeros to the table, and continue with the loop. In the first forward, we will create table I comma j, where I is I plus 1 comma j minus 1 minus table I comma j minus 1, and in the backward difference we have I comma j is equals to I comma j minus 1 minus table I minus 1 and j minus 1 respectively, and return table for forward or backward. The use case is Newton forward formula, Newton backward formula, and finite difference formula. Now we have last Newton interpolation formula. Newton interpolation formula in which we import numpy as np and math as com. Then we create two functions, Newton forward and Newton backward. Table should be equal to the forward difference table. In the previous question we create this table and initialize s equals to x minus x0 divided by h in the Newton forward, and return the result. Similarly, in backward, we return the compute result. The section 3 that we have is numerical difference, the interpolation based finite difference. Let's start with this. We have numerical difference. Here assumptions are f of x or tabular data given should be given, equal and unequal spaced, small h for accuracy. The geometrical interpretation say that forward we have slope xi comma xi plus h, and backward slope for xi minus h comma xi. Central is more accurate, and Richardson is eliminated. The time complexity for is O of n and O of n. Then here we create a table, take all the inputs, we create a nested loop for this in which we initialize dl to 0, and if k is not equal to I, we initialize pod with 1, product with one, and for another we have range in n, and if j is not equal to I and j is not equal to k, we perform the following operation and return the derivative. Let's move on to the next topic. The section 4 is numerical quadrature, in which we're going to see Newton's Cotes formula and Newton quadrature formula. Numerical integration with Newton quadrature formula. Here we have to assume some assumptions, which is f is integrable on a comma b and sufficient smoothness. The geometrical interpretation state that we have three formulas like trapezoidal, Simpson, and Gauss. Trapezoidal is area of trapezoids. Simpson's determine the parabolic arc, and Gauss provide us optimal node points. The time complexity for Newton codes is order of n and Gauss of order of n. The error that we get in trapezoidal is order of h square. In Simpson, it's order of h to the 4, and Gaussian is exponential decay. Here we have the code for the same. We import new numpy and we create three different functions for trapezoidal, Simpson, and Gauss literature. We take all the required things as an input and perform the respective task. In the fifth section, we have to solve system of linear equation with three given methods, which is Gauss elimination, Jacobi iteration, and Gauss-Seidel method. Let's start with Gauss elimination method. Assume A is n cross n non-singular matrix and no zero pivoting or partial pivoting enabled. Then we have system AX is equals to B, geometrical interpretation, transform A into upper triangular matrix, and back substitution for X. The time complexity for the Gauss elimination is order of n cube and space complexity is order of n square. Now we started pivoting. Pivoting is partially avoided dividing by the zero. Here is the code for the same. Here we create an function Gauss elimination. We take a and b as an input, n equals to b length, and convert our matrix into upper triangular matrix by using forward elimination and backward substitution. The next we have Jacobi and Gauss-Seidel method, Gauss-Seidel iterative method. Here the assumption we made is A should be diagonal dominance matrix and guaranteed conversion is promised. Geometrical interpretation, Jacobi for all the odd values, Gauss-Seidel for mix old and new values, and Gauss-Seidel conversion is faster than anything. The time complexity that we have here is order of kn square, where k is the number of iterations, and space complexity of order of n square. Now the conversion in Jacobi is slow but parallelizable, and in Gauss-Seidel is 2x faster. Here we have the code for the same. We have two different functions, Jacobi and Gauss-Seidel. We take all the required thing as an input, as an argument, and perform the respective task for the same. The sixth section we have approximation method, in which we have least square and orthogonal polynomial approximation. Let's see both of them. First, we need to assume in this data may be occurring noise with error and minimum sum of square. Then we have geometrical interpretation, which is the best fit for the curve, not the exact but the best fit. Minimize ax minus b to the whole square, and we have normal equation. The time complexity are the following. Here we have the code for different things. First we have least square. We take all the required thing as an input and initialize a. We calculate the coefficient with the following method and return the coefficient as a result. And then we have def literature. Here we take all the required thing as an input and map them and return the coefficient. Last we have ordinary differential equation. Here we going to see Euler method, Runge-Kutta method, Picard method, and Taylor series. First we start with Euler method and Runge-Kutta method. The assumption we need to make is dy by dx is equal to f of x comma y. The initial condition of f of x0 should be equals to y0, which should be given. The geometrical interpretation is Euler create tangent line steps and Runge-Kutta method is weight average of slope at the start, mid, and at the end. The time complexity for Euler is order of n with one evaluation per step, and Runge-Kutta method for takes the time complexity of order of n with 4 evaluation per step, which is more accurate and more fast. Let's see the code for the following. Here we have two codes, Euler method and Runge-Kutta fourth order, which takes all the required thing as an input, perform the task. In the Euler, we directly perform ys is equals to ys I minus 1 plus hf xs I minus 1 and ys I minus 1. And Runge-Kutta we calculate k1, k2, k3, k4 and compute them. Then we have Picard iteration, application method, and Taylor's series. The assumption we made is the similar like the previous one, that dy by dx should be equals to f of x, where y of x0 should be equals to y of 0. The Taylor f has many derivatives. Geometrical interpretation, Picard successive approximation, and Taylor is y expansion series. The complexity for Picard is O of k, where k is the terms, and for Taylor it's O of p terms per steps. Note: Picard mainly theoretically, and Taylor required high accuracy, which is neutral symbol. Here is the following code for the same. We have different function for the different method. We take all the required things as an argument and perform the following. Here is the comparison of all the time complexity, space complexity, and their conversion rate for all the methods are the following. So that's it for this presentation. Hope you guys like it. Uh, Thank you for giving me this opportunity.